recording from yesterday onto YouTube as well. But I just did that, so you may not have seen it yet. And it's posted on Slack. So in the past, we've looked at various Python libraries like NumPy. We looked at pandas 2 days ago for our data in table form. Now we're going to look at 2 packages called xarray and dask. So xarray is very similar to pandas, but it handles multidimensional data sets rather than just tabular data sets. And it actually works together with dask. And dask is really what makes analysis of large data sets possible. So they work together to do this. So xarray is pretty much used for any climate or ocean model or anything like that. That's at least what I know. It's used for a lot of other things as well. When you have things like you have your latitude and longitude in the horizontal direction, but you also have depth. So you have 3 physical dimensions, and then you have all of those points. You have different values at each point in time as the model steps through time. So then you might have something that's 4-dimensional, or sometimes you get even more. So there are some really good resources here, and this is actually from my postdoc advisor, Ryan Abernathy. He did a research computing class back in 2018, but a lot of it is still very relevant, and it has a nice overview of how to use xarray and dask, but specifically for like the climate sciences. So I recommend using those. So we'll do a quick demonstration of this stuff. So we are going to load in data from the cloud. In this case, we're using the Community Earth System Model, CESM. Oh, I should zoom in. And we're using POP, so that's the Parallel Ocean Program. And we will load that data from the cloud. And we got this code from the Pangeo data catalog, which I've mentioned before. And all of the data sets in the Pangeo data catalog you all have access to right now in the hub, and you will for several weeks. Okay, so we've now loaded something called DS. So we have DS equals, and then this is, you can kind of ignore exactly what this says. This basically means you're loading a data set into something called DS for data set. And now, if we type DS, then it will print out all of the information about DS that we want to know. So we type DS here, rerun the cell, and we wait a few seconds, here we go. And then it tells us right at the top what type of variable this is. So DS is, referring to something, and it refers to an xarray data set. So that's just terminology. And an xarray data set contains many different items. So the first is it has dimensions. So that are things like latitude, which is like nlat, longitude, nlon, time. And then in this case, we actually have a bunch of different depth or z variables. And so these are the dimensions. You've got a giant list of coordinates, and these are things that are all useful to have, like you have T area, which is the area of all of the T cells. We have different cells because they're staggered grids. So if you've seen Joseph's presentations, kind of recorded lectures on ocean modeling, or if you attended his Q&A, probably, you might have seen that they're kind of staggered grids in ocean models. So that's what I mean when I say a T cell versus a U cell, and they're just slightly different terminologies with different models. We have DXT here. That's, well, actually, we can look at what it is. If we look at DXT, then we can see that the dimensions are latitude and longitude, so it's 2-dimensional. And then if we go all the way to the end here and click on this paper icon, we see that it's the X spacing centered at T points. So it's the X spacing between every T point in our grid. And it tells us the units as well, which is centimeters, very handy. So this is kind of a nice way to visualize the data in these tables like this. So it's very similar to pandas, where we could visualize all of the data as a table. Whereas here we've got so many dimensions and so many variables that we can't see it all as one table, but we can see individual items, like individual coordinates in this table form. And if you go and click on this cylinder off to the right, it shows kind of a graphical representation of what we're seeing. So it says you have a two-dimensional object, so it's basically a rectangle with this length on each side. And then over here you have the full array. Bytes means like the size, so we have 69 megabytes. It tells you the shape, and then it tells you a few other things. It also tells you the chunk size. Because 69 megabytes isn't very much, it's all one chunk here. So these are identical. But if this were a much bigger variable, they wouldn't be the same. So that's kind of how we read everything here. If I scroll down, we see another one of the items in our data set is data variables. And we can see all the variables listed here. So if we look at sea surface temperature, for instance, which is SST, we can see that it's three-dimensional. So it's time, latitude, and longitude. And then if we go over here, we can click on the paper. It says, sure enough, this is the surface potential temperature. Units are degrees Celsius. And here we can look at the size. And here we see that it's three-dimensional. So we've got this three-dimensional representation. And now we have the full array, which is 517 gigabytes, but we have chunks that are much smaller. And it tells you what the chunk sizes are. So in this case, one chunk is one time step because this is the time dimension. And there are also attributes. And so these range from data set to data set, but some of them are quite useful. Let's say I pointed one out yesterday that was quite useful. Oh, here we go. So calendar says all years have exactly 365 days. So that's telling me that there are no leap years in this data set because a leap year has 366 days. So it has, depending on the model, some of these are more useful than others, but it can often have some useful information for the user. Yeah.
Yeah. So please, when you show the dimensions of a particular variable, and you will see the 3,600 length by maybe 2,400. Are those the 3,600 represents the number of longitudes?
Yeah, exactly.
Okay. Okay. Okay.
Yeah. So if you so here it doesn't quite have them labeled. But if we scroll all the way up to the top, it says here. So nlat actually means the number of latitude points. It's 2,400. Okay. And number of longitude. So for this particular data set, instead of having the actual latitude and longitude values as a dimension, it's just the number. So it's just kind of like 1, 2, 3, 4, up to the however many there are.
Okay.
That's what that is. Yep. And then you can see that time is the much longer dimension here in this particular case. Yeah, so sometimes it is really nice to kind of see this visually, I find. This kind of how to visualize this is quite nice. Okay, so if we want to just access one variable, say SST, well, I already evaluated this from yesterday. We can just say ds dot, and the dot is kind of saying we're accessing what is in ds, which is our data set. So I'm going to say ds dot SST, and we get this information here. So we get that it's an xarray data array. So you might remember before we had an xarray data set. So DS itself is a data set. Sorry, I'm getting a bit of background noise, so I'm just muting someone. As always, you can unmute yourself to ask questions. But when you're grabbing this variable, it's just a data array. And a data set is made up of all these different things and so a data set is made up of many data arrays. And so here we're just looking at one data array. So it's just like one array of data, hence the name, data array. And we can see that it has 3 dimensions. It basically gives us all the same information that we just saw up above. We get the same representation here and all the same information. But that's how you can access it if you want to refer to sea surface temperature. You can access other things that aren't variables. So time is a dimension and coordinate. So you can say ds.time. And again, it's a data array. Here you can see that it's got some words here. This just means that there's a convention for how to denote time, and there's CF time, and it uses that. And then here it tells us what we kind of saw before. Date time no leap is a type, like a data type, basically, where there's no leap year, which we saw before. Okay, so I'm going through pretty quickly. So I know for some of you, this might be quite a lot. So please stop if you have questions as we go. This was just to show that we can print out all the dimensions as well. It's not in a nice table format, so it's probably less useful, but here are all the dimensions listed. So we've got our nlat, we have nlon, and then it has the size of each of them. So we can access the SST variable by saying ds.sst. And we can add to that if we only want the first time step, for instance. So we only want like time equals 0, which is the first one, because Python starts its indexing at 0. Then all we have to do is say dot icell. So that's selecting based on an index. That's why it's icell. And then say time equals 0. And if we evaluate that, then we get this here. So notice before when we had SST, it was 3-dimensional and it had time as one of the dimensions. Now time is gone because we selected a single time step. So there's no more dimension in time. And it's just a 2-dimensional object. So that's how we can select that. We can select more than one time as well. And we do the same thing, but we put in this function called slice. So you're saying, I want to slice these values, so from 0 to 10 of the data set. And so then it will give us 10, a time dimension of length 10. And we can see that represented visually here. Okay. So we can do some other, so instead of just selecting specific time range, for instance, we can also take a mean. So we can take an average over a dimension. So if we want to take the sea surface temperature at every single point in time and average over all of that, all we need to do is take our SST again and say dot mean and then put time in here. So that plot should not be there at the moment. So if I evaluate this, then it will give me back this representation again of all of the metadata, which is everything that we've been looking at so far is all metadata. So we haven't actually seen any data itself, like any actual numbers of what SST is, but we have been seeing this metadata. And when you first start, that's kind of what you want to know. What variables are there? How big are they? You know, all of that kind of stuff. So now, if we actually want to see some data, we have a few options. So one of them is if we call dot plot. So this was what we took before when we selected just the single first time step of SST. And then I can say, I can just add dot plot with these two parentheses with nothing in the middle, and it will plot that for me. And we can see that here because I pulled it up yesterday already. So you can kind of see how xarray makes things really nice, where you can just kind of keep adding things in a single line, where you say, I want to access the data set. I want to grab this variable. I'd like to select the first time step or the 0th time step, and then I'd like to plot it. And so you can do that in very few typing strokes and all in one line, and you can plot some data. And the other thing that we notice is that the plot has done some interpretation for us. So notice that we have the X and Y labels here for nlon and nlat, and we didn't have to specify those. We didn't have to say label the X, X-axis to be nlon. It just did that for us. It also made this nice color bar for us and said what the color bar is. So it says this is surface potential temperature, and even puts the degrees Celsius, so the units there. And that's because xarray has this all built in for us. When we say dot plot, the default is to read the metadata associated with our variable, which is SST. And so when I'm plotting, it says, oh, well, we know the x-axis is nlon. We have that label there, we have them connected, so we might as well label it for the user. And the same thing here, it says we know that surface potential temperature is this color bar, and we actually know the units because we saw up above that the units are included here. And so it does a lot of this interpretation for us, which is really handy. Okay, we have a question. We have a global SST map. Yep. How to select, for example, Gulf of Guinea? Yeah. Okay, that's a good question. So this, yeah, it is, Daniel. I'm glad you see this. Xarray is like, makes your life so much easier. And you may still want to change some things if you're making a presentation, and you could change things, but it's nice that you pretty much have a plot ready to go from this one line. So what Amemu, your question is, it kind of depends on the model. So in this case, when you have nlat and nlon, we don't actually know the latitudes and longitudes by looking at this. So we could try. We could say, oh, let's see, Gulf of Guinea maybe starts at what, like nlon is 900. So we could kind of do it like that. And we could say nlon equals slice from 900 to 1300. It's probably gonna be a bit off. And then we could do the same here. Let's say 1000 to 1400 or something. Nlat equals slice 1000 to 1400. So this should slice out, if I've typed it correctly, I think I have, this specific region for us. So that's kind of the way to do it through xarray. If you want to get the exact latitudes and longitudes, different models do it differently. If we go back up here, this has, for instance, a T-lat. If we see what that is, it says it's the array of the T grid latitudes. So you can actually match up the latitude, and there's a T-long and the longitude, and actually do it that way as well. But you would just slice it like I did with time to create a plot like this. And you also see that the color bar changed. And that's because xarray has these defaults. So if you have a field that is both negative and positive, it tends to default to the one we had before, which was kind of a blue, white, red, where white was in the middle and was 0. So it's kind of even on both sides. If you just have a positive value like this, where it just ranges from like 19 to 29 or something, then it defaults to this color bar. So it has all these defaults built in, and you can change any of these. So we could actually change it now. In our plot function, I could say CMap equals, I don't remember what any of them are. Blue, white, red. I think that's one of them. So you can look these up, what the color maps are in PyPlot, and there we go. So I just said I want this different color bar. So you can adjust, and you can adjust anything like that. I'm doing the same thing. And actually, so that's actually a good point. I don't think I mentioned that yesterday, but when we do our PyPlot plotting from before, where we say, plt.x label and label the x-axis, you can do all of that within the plot function here. So this, like CMap, you can do it all here, because it uses PyPlot as a backend. Xarray does, and so it's all the same. Everything is the same, which is very convenient. Okay, I hope that answered the questions. And yep, so you can make some nicer plots. This we can kind of see because we have the, we can see the land, but Cartopy is a great plotting library that will have a tutorial on Monday. And that will be with Josue. he was a little bit involved in the school last year, if any of you were here. But he's really good with visualization, and he's very, and like animations and that kind of thing. So if you're interested in that, I really recommend going to that. He's been putting in a lot of effort into that tutorial this week. Okay. Cool. So that was just like a very, very beginning introduction to xarray. Now I'll quickly go through dask. So again, sorry for those who've been here before. Hopefully this is helpful still to hear these things again. So dask, as I said, so it actually has two kind of different parts. One of them is it basically allows you to run code in parallel relatively easily. So you may have heard of parallel computing, which allows for things to run fast. So instead of doing one computation, waiting for that to end and do another one, if they're completely independent, we can just split them apart and run them at the same time. And so it saves you a lot of time in running things. So it does that, but it also, this is where it kind of works with xarray to deal with, as I say here, larger than memory data sets. And we'll see that kind of at the end. I'll come back to that. Okay, I'll start with the parallel computing bit. And this is just an example, a very like toy example here. We're just going to write two functions. This is how you define a function in Python. You can read more about functions if you're interested. If it's something that you're going to do a lot, it's nice to define something as a function, and you just say def, like define, and then I'm going to call my function add, and add takes two arguments, x and y. And all it does is I call this function sleep from within the add function, and all this does is pause for 2 seconds and do nothing. But we're doing this so that we can see the speed up time. So this is a completely useless function for most situations that we probably won't use, but we're using it here. And return means when you call this function, what do you get back? You're going to get back the sum of x plus y. Similarly, we define a function MLT, which is a multiplication. It sleeps for 1 second and gives back x times y. So in this cell, we run, well, and I've already run it, so you can see that. We define 3 variables, A, B, and C. And A is the output of the add function for the numbers 1 and 2. B is the output of the MLT function, the multiplication one, also for the numbers 1 and 2. And then C is the output of the multiplication function, but of A and B. So A and B, so if we run this cell, and this is a kind of special function. If you put %% time at the top of your cell, of any cell, it'll tell you how long it took to evaluate that cell. So I use that a lot, just so that you know how long something's going to take. So if we calculate this out, we have one of the add function, which has a 2-second delay. And then we have 2 multiplications, which are each a second each. So it should be 4 seconds total. And when I ran it yesterday, it was indeed 4 seconds. So that's just kind of running some basic code. Now, if we use dask, don't worry too much about how we're using dask right now, but just we're using this function in dask called delayed. And we are going to run the same thing. This is just the syntax for running all of these with dask. And so, well, we're going to run it. And when I did this yesterday, we see that the wall time is 758 microseconds. That's a very short time. And in fact, it's so short that like no computation could have been done in that time. And that is correct. No computation was actually done. And that's how dask works, is it takes these computations, whatever code I write, and it basically, when I write this and I have A, B, and C, it stores these kind of graphs or these charts on how to do the computation, but doesn't actually carry it out. And it only carries it out when you call it at the end. and do something like this, where you say dot compute, then it will compute, for instance, C. So here we're saying we want to compute C, and then it will actually do the computation. So if we notice, C depends on A and B. So A and B have to be computed first before we can compute C. However, A and B are independent of each other. They can be computed at the same time. It doesn't matter because they don't have any interdependencies. So A takes 2 seconds, B takes 1 second, but it has to run at the same time as A. So we've got 2 seconds total, plus the 1 second to run C. So when we compute C, it's a total of 2 plus 1, or 3 seconds, which is exactly what we saw when we ran it. It's wall time. So in this case, we sped up our calculation from 4 seconds to 3 seconds, which sounds like very minimal, but you could imagine how you could scale this up. And instead of shaving off seconds, you could shave off minutes, hours, weeks, months, when you're running all these things in parallel. So that's a brief demonstration of the first aspect of dask. And we use it in a very different way when we're computing big models. We can look at that again. We looked at that at the very end yesterday. So the other thing we'll get to that here. So the other thing with dask is that, so kind of the second part is that this is where it works really well with xarray and allows for manipulation of larger than memory arrays, meaning you have really big data. And you can't possibly load it all in to even look at it because it's too big. So if I print out again this data set that we had from above when I was going through xarray, so we had this data set called DS, it's our xarray data set. I'm printing it out again just to show you that, so remember we looked at SST and we saw that it had 3 dimensions, time, latitude, longitude. And if you keep going, it actually says here in this gray, dask.array. So what this actually means is that the SST variable, and actually all of the variables here, are actually dask arrays, and xarray is what we call a wrapper. So at the core, SST is a dask array, and then xarray wraps around it. And so it's xarray that allows us to write down computations and have them only be evaluated when we, for instance, say .compute, or when we plot, like we did above. When we actually plotted, we could see the data. And xarray is kind of the wrapper around that keeps track of all of the metadata associated with all the variables, with the whole data set, with all the coordinates and everything like that. And that's how they work really well together. And you can also see here in this dask array, it's through dask that we have these chunks. And so the chunking is done through dask, and we saw that before, where in this case, each chunk is 1 step in time, and then the entire globe. Okay, so that was a very, very quick overview of xarray and dask. Any questions at this point? We'll move on from here and see them in use with ECCO data, which might help you to see how they can actually be used in data analysis. But any questions at the moment? Okay. Cool. So yesterday we went through this notebook. We might go through the other one today. The other one does not use dask's computing power. It does use dask through the xarray. But so if you want to see how we use dask, you can scroll down here. And it says speeding things up with a dask cluster. And this is the code to run that. Unless you all really want to see that now, I think I will go to the other ECCO notebook and go through that, it's very similar. It's just slightly different examples of what we could do with ECCO data, for instance. So those of you, hopefully you all know what ECCO is or have attended Dimitri Menemenlis's Q&A session or watched his pre-recorded lecture. If not, I do recommend it. The pre-recorded lecture gives you a nice overview of what ECCO is. It's pretty great product, and you have access to it right now very easily through Jupyter Hub. He also is doing another Q&A next Tuesday, I believe. Let's look at the schedule. Yep, so he's doing another ECCO Q&A on August 3rd from 11:30 to 12:30. So join the ECCO Python 2021 Slack channel if you're interested in that. So ECCO stands for Estimating the Circulation Climate of the Ocean. And I might slip sometimes I call it a model, but it actually combines aspects of ocean models with ocean observations to provide what they call a state estimate. And it's quite a unique product in that sense. I won't go into that too much. That's where you can learn from Dimitri and from his pre-recorded lecture. But we are going to do a bit of analysis on it. This notebook was, I just adapted this notebook from this resource here. So it's the ECCO version 4 tutorial. So it's version 4 of ECCO is the current release, although in his pre-recorded lecture, it's mentioned that version 5 comes out later this year. And this has so much information. So if you're really interested in this, I really recommend reading through this. It has, getting started here. You can click on all of these links. And then it goes into the data structures and, really everything. And it has these examples of what you can do with ECCO. Sorry, there's a question in the chat. Is the tutorial available for us to read? I don't know which tutorial you mean. Did I mention? So there's this one here is absolutely available. I can link to it. I'll post this link in the chat if this is what you meant. If not, let me know. Yes, so the link that I just posted is the link to this, which is the ECCO version 4 tutorial. And by tutorial, they kind of mean everything you might want to know about ECCO. So it starts by saying, what ECCO is, and then it has a list of Python packages. And, you can click on any of these. So just know that a couple of these are a bit different because we have our Jupyter Hub. So for instance, downloading the ECCO v4 py package, which we are going to use in a second, you don't have to do that because it's already installed in our Jupyter Hub. So that's really nice. But anyway, if you want to do all this on your own computer, here, the instructions are all here. Cool. I hope that made sense. Lots of really good information there. So I pulled one of those over into the cloud. Into our Jupyter Hub, which runs on the cloud. And we're just going to do a couple, what they're calling kind of scalar calculations. So just some basic calculations of what you might want to do with an ECCO dataset, or really any ocean model. So as usual, we import all of our libraries to start off with. So in this case, we're importing NumPy, which is numerical Python. We've seen that before. We're importing xarray, so we're using that.
Can you zoom in a bit?
Oh, yes.
Could you zoom in a bit?
Thank you. Sorry.
Sure, no problem.
I have mine on this really big screen because this is where I work from home. And so
okay.
I apologize. For me, I can see it fine, but yes, thank you. So we're using xarray. We're using the plotting package, so pyplot, which we saw a couple of days ago. And then this is the new one, which is ECCO specific. So it's ECCO_v4_py. So it's the Python package for version 4 of ECCO. And we're just going to load it as ECCO, just so we don't have to type out the whole thing. And we saw this before. We're importing the warnings library so that we can ignore all of our warnings. When I do my regular research, I don't do this, but it's kind of nice to not have warnings pop up when we're doing this. Okay, so I will evaluate this cell, Shift Enter. And we see the little star over here. So that's going. hopefully it will run. Yep, so now it says number 1, so that's good. So we loaded everything from there. And now we're going to load ECCO from the cloud. So this is very similar to the code that we had previously where we're looking at CESM data. And again, I just copied over this, this code from the Pangeo data catalog. So you don't have to memorize this. And we're going to call it ECCO monthly DS. So this reminds us that this is a monthly data set. There is a daily data set, although I don't believe that that's on the cloud. So we're just going to be looking at monthly. So I'll run that. And while that's running, we will put our use, our knowledge to use. So first of all, we can see that we just ran that and it says we've got an xarray data set. So it's just like we had before. And it prints out all of these things, our dimensions, coordinates, data variables, attributes. Actually, there are no attributes here. But remember, this is where we're making use of this xarray plus dask combo, where we didn't actually load any of the data. We just loaded all of this metadata, which is all the information about the data set. We can see here that there are different dimensions than in the previous model. So here we have something called face, which we will see later what that is. I is our kind of longitude, so like X direction dimension, and J is the latitude one, so the other horizontal, like the Y dimension. And then K is depth. And we've got a few other kind of versions of K and of the I and J. And that's because we have this staggered grid. So different variables are saved on slightly different grids. And that's to make the computation a bit easier. And that can be explained by Joseph if you watch his lectures and look at those slides. It's also explained in the ECCO tutorial that I linked to in the chat. And then we see that there are 288 time steps. It's a lot fewer than our last one, which had 14,000, but that was a daily data set. Okay, so if we go down here, let's say we're only interested in a certain time band. So let's say this data set starts in 1992, but let's say we're like, no, we don't want 1992. We just want starting from 1993. Then we can say, do what we did before. So here we're kind of redefining our same variable that we had before, ECCO monthly DS. And then we do dot cell, so dot select. So in this case, we're not using the index. So we're not using iCell, we're just using cell. So we're just selecting. And that's so that we can say we want to slice between these years. So instead of saying an index like 42, which we don't quite know what time that would correspond to, we can also do it by labeling the actual time, in this case, by year. Cool. I just noticed there's this mismatch here with 2015 and 2018. So there's a typo. If you're following along, you could change it. It actually doesn't matter in this case because the data set only goes up to 2015. So when I say 2018, it'll just stop at the last value. So it doesn't matter. But anyway, that is a little typo. You can put 2015 there. Okay, so I'll evaluate that. And I type out ECCO monthly DS at the bottom of the cell, and then it'll print it out for me again. So now we can see instead of time being 288 long, it's 276. And that's because we chopped off 1 year. Okay, and so one other thing that we need to do. So I've mentioned this before when I was talking about cloud computing. When we put data on the cloud, we actually are saving it. We have to manipulate the data a bit to be able to save it on the cloud. And cloud data is typically stored as, or this multidimensional cloud data is stored as ZARR, Z-A-R-R. And all of the files stored on the NASA server, which is where ECCO is run and stored initially, are netcdf files, I believe. And so there's some conversion that needs to be done. And in this case, for some reason, the person who converted it renamed something that was called tile in the original data to face. And I have no idea why that happened. There are just a few inconsistencies. So this is just a trick so that we can rename what we have currently loaded from the cloud. It says face, and I'm saying, please call it tile instead. And so this is this dimension here, face. And I'm doing this because the ECCO v4py library expects something called tile, and it gives us an error if we have something called face. So this line here is something that I added as I went through. I had to go back and add this in, which you'll do a lot while coding. You know, we're going through very linearly, but I code very non-linearly, where you go through and you realize, oh, this is erroring, but it gave me a very specific error, and it said, this data set does not have, had an unexpected word called face. And so I knew immediately that the function I was trying to use from that library did not know what face was, which is one of the dimensions. And so I said, okay, I have to rename face to tile because that's what it expects. So if we run this, now we can see that over here, we now have something called tile, and face is gone. So we've just renamed it. So you can do this anytime. It's quite easy to do. Okay, so now let's do some calculations.
Quick question.
Yeah.
I noticed that you had, when you did the slides, you had time and then time underscore S&P.
Yeah.
Did you need that one as well?
Good question. That's another one that I went back on. So time SNP is, I forget exactly why it's there. This is where different data sets are different, and I'm not super familiar with ECCO. I don't think we ended up needing it in this notebook, but there were some other added things at the end of the original tutorial where I did need to have this one also be the same size. And so we might have needed it here. So this was another case when I went back and it said something that time SNP is the wrong size. And I went, oh, okay. So I went back and added it here. Yeah.
Right. Yeah.
So yeah,
No
apologies. We don't actually actively use it. So I don't, it was like a backend from a function.
Sure.
So
Sure.
yeah,
That's
don't
fine.
actually
Thank you.
know exactly what it is. We could just look that up.
Yeah.
Yeah, but so
Thanks.
you can slice, anything that you want. So here, slice those two. Okay. So let's do some calculations. So let's say we want to get the global mean sea level. So that's something that's of interest these days, with sea level rise, all of that. So let's just see what the mean sea level is from the time frame that we selected, 93 to 2015. So here's where we can see one of the benefits of notebooks. We can put the equations, our mathematical equations, right in line with our code, as well as this write-up. And so here we see that it gives us the equation for the global mean of SSH, which is sea surface height, as a function of time. And so we want to sum over all of the SSH values, multiply by A, which says here is the area, and then divide by the total global area, total area of the global ocean. So this area here is the area of each cell in our grid, which varies, which is why we need to weight the sea surface height by the area of each cell. And that's why we multiply here. And then it says the area of the global ocean is just defined as the sum over all of the areas of the individual cells. So let's do that. So you can read some of the things here. It mentions that SSH is a sea point variable. That is, again, the staggered grid. That's bringing up the staggered grid. Let's see, I think I have this open. So this is from the ECCO tutorial that I just linked in the chat. And it shows you the grids here. So this is kind of in a 3D version. This here is looking down on the grid. And you can see that the center of each of these squares is a sea point. you have U points in green, and you've got V points in purple or pink, and so on. So we won't go into that now, but that's what it means by C point. Okay, so first of all, we want to make an ocean mask. So that's so that we can mask all of the land cells, and we only want to calculate the area, for instance, of the ocean cells, because we only care about the ocean. We're not looking at land right now. So we create this ocean mask. So as it states here, we'll construct a mask that is true for model grid cells that are wet, aka ocean, and false for cells that are dry, aka land. And we do that by using this coordinate here called HFAC. That's hard to say. And so when I went through this, I looked at this code and was like, whoa, what is that? I don't know what that is. So I scrolled back up, clicked on coordinates here, and looked through and said, oh yeah, there's HFACs listed here. It looks like it has 3 dimensions. So it has K, it has tile. So that's after I renamed face to tile. And it has J and I, which are the Y and X dimension variables or dimensions. And tile is something, well, we'll see that in a second, what tile is. Will we, or was that in the previous one? Well, tile is that basically the way that ECCO has stored its data is it just has individual kind of tiles when you do a plot. Maybe I can pull that up from here. So this is when I just plot the data in tiles, it looks like this. So you just have tiles, which is basically just different regions. So that's what we mean by tile, which is why we have this extra dimension. And that's just a feature of ECCO. I've never seen another model that does that. Okay, so we see again, we have a dask array. We can click on this little paper icon and it says it's the vertical fraction of an open cell. So basically this is saying the fraction, it's giving us a fraction of kind of, I believe, of the wet and dry cells. And that's why we're using it to figure out what our ocean points are. So here it explains that, and it says HFAC is between 0 and 1. And it's for cells, sorry, it's 0 for 100% dry cells, meaning it's 0 if the points are on land, and it's 1 if the points are completely wet, or it's some fraction in between if it's a cell that has a fractional amount of ocean. Sorry. Okay, so we're going to use that to make our mask. So in this case, we want to say we will consider anything that has a non-zero HFAC. We're going to consider that to be an ocean cell. So even if it's partially land and partially ocean, we're just going to say that that's ocean. And so down here, we define the mask. So I say ocean mask. We call the data set. We say .HFAC, .I cell. So we're selecting based on, sorry, I'm getting some background noise. Selecting based on the index of K. So we want K equals 0. So K is the depth. So we just want the top because we want the sea surface height. So we're only looking at the top. And then we're going to use this function .where, which basically says we want this mask where all of this, all of these only where this holds true. And this, what I've highlighted, is our data set the HFAC. Again, choosing the top layer where all of that is greater than 0. So that's how we make our ocean mask. And then again, we see that well, our ocean mask is 3-dimensional in this case because we have this tile dimension. And that's our ocean mask, which we will then use. So let's plot the ocean mask. So now you'll actually see the tiles as well. So just zoom out a tiny bit. We just plotted the ocean mask, and you can see all of the tiles here from 0 to 12. So there are 13 total. And we see that there are 2 colors. So white is land, clearly, and the other color is ocean. So this is the mask that we can use to make sure that we're not calculating anything over land values. And the white actually means the land values have been set to not a number, to nans, which we saw in our pandas tutorial. And that's how we do the mask. So anything that's not NaN is ocean. Okay, so to actually calculate the area of the ocean, we're going to use this output RA. Let's go back up here and see, oh, we can just do it right here, what RA is. So we have this RA. It's tile and JI, so it doesn't have any depth or time. And if we click here, it says it's the cell area. So this is the area of each individual cell in the grid. So if we go back down here, we're calculating the area of the ocean by saying we want all of the areas of every cell, but only the ones that are not land. And so to do that, we multiply by this ocean mask that we've just made. And then we sum over all of it to get the global mean. Oh, to get the global number, global area, not a mean. So that's how we do that, total ocean area. And then here are just 3 fancy ways of writing it out, which we can see. So we have total ocean surface area in meters squared is this long number. We could write it in kilometers squared. And you can see how they've done this here. And then we can also write it in scientific notation. So this is just kind of some Python learning. If you're interested, you're welcome to look at that. So great. So now we've calculated the area of the ocean and we've stored it in this variable called total ocean area. We will ignore that for now. Okay, so
Paige,
yeah.
Are these codes you copied from the tutorial or codes you had to write by yourself?
So these are ones that I mostly copied and adapted. I took out some things that I didn't think were useful, and
that's a lot.
Yeah, they actually used a lot of NumPy functions instead of xarray functions, which can slow things down. So I converted several of them to xarray. But basically, at the moment, I didn't write any of this. And part of that is because I'm not super familiar with ECCO. This is the first time that I've used an ECCO dataset.
Yeah,
but I write these codes for other, I use the CESM model at the moment. And I do write that. And a lot of these, are just kind of generic. Like we could do this for any model. We could say, find whatever coordinate has the area of the grid cell. You need to make sure you're not counting all the land cells, and then sum, and say dot sum to add them up. So,
okay.
So yeah,
a lot of work.
Yeah, in a way. So it seems like a lot, but I think the more that you see, especially like some of these lines in xarray, like we're using right now, you kind of get to know. I know, the dot mean, dot sum. You can always do that. Doing an ocean mask is quite common. So when you see that once, then you kind of know how that's done. So yeah, it is a lot. But as you start to see things, you'll kind of figure out.
Becomes familiar, yeah.
Yeah. There are a lot of things that are familiar even across different data sets. And using dot where, I do this a lot. That's a really nice function in xarray. Yeah. So I think for me, the hardest thing at the moment is I don't know what all the coordinates are. So when I was looking at this code, I kept having to be like, oh shoot, what's that? And having to go back and look. But that's why it's nice to have this visual representation that xarray gives us. where we can just say, oh, what's this? Yeah. Okay, so we will continue on, and we're going to do just some very similar type of stuff. So you'll see kind of the same xarray computations again, are very similar ones. Okay, so now we're looking at the global mean of sea surface height, which we saw before. So we've calculated this global mean, global mean, sorry, the global ocean area. I keep saying mean, but it's not. It's global ocean area. So now we want to look at this numerator. So we want to sum over the product of SSH and the area of each individual grid cell. And here, sea surface height is given by this variable called ETAN. Again, something you need to know the data set for. So this global mean, we're going to say, I want to take the data set, I want to take the sea surface height, and I'm going to multiply it by the individual grid cells, this RA coordinate, which we saw before. And then I'm going to sum that. So you're doing the sum on this numerator. So say dot sum, and you can specify which dimensions you want to sum over. So here I say I want to sum over I, J, and tile, so all of the horizontal dimensions. And then I divide by the total ocean area, which we calculated above. This is just an example. You can add units. So if you have I just created this new variable, SSH global mean, and let's compute that and then print it out. Okay, so we just created this new data array and printed it out. It keeps the coordinates, but it doesn't have any attributes in it yet. So here we're adding an attribute, and it's called units, and the units are M. So let's print it out again. So if we do that, scroll down, now we have one attribute called units, and the units are M, so meters. And now we can plot it, as it says, plot for fun. We're saying we want the color to be black. That's what this K means. And this takes, I think, 30 seconds, something like that. So that'll take a little time. There we go. So this is the mean sea surface height averaged over the globe at every point in time in this data set. So it's every month from 93 until the end of 2015. And so we can see that there's a very clear trend, isn't there? Cool. So that's an example of what you can do with ECCO data. Kind of continuing from here is kind of more of the same kind of things, making some nice plots, making use of this function that's in the ECCO library. So we can keep going with that. I have about 15 more minutes before I will have to leave. Should I just keep going? Does anyone have any questions, or would you like to look at anything else or anything? Is there any feedback from all of you? What would be most helpful? No preferences?
So I was in Dr. Anson's tutorial,
yeah,
and
great.
I'm just thinking about how to compare or use the data from the model and compare that with in situ data. So for instance,
yeah.
the tutorial we had before this, I think we plotted, was it sea level? We plotted a map of sea level, but the daily data for each and every point in time, it has been averaged over an entire day, where if you took data, institute data, it will just be an instant of time. So maybe you took it at 3:30 p.m.
Yeah.
How do you use both? So I don't know whether it's a combination of yourself and Dr. Anson will answer, or if the question is not for this, I mean, it's not for this session, I should take it to his session or something. I don't know. Or just something I'm just thinking about.
Yeah, that might be more of a question for Joseph. Is that a quick answer, Joseph, or should we wait until your session next week?
Oh, no, I mean, I think it depends on what you want to do, right? So in this case, the data here is monthly, which means that if you have daily data from your in-situ instrument, you need a lot of it to be able to average and have monthly points and compare it to this, right? On the other hand, if you had a model that will output daily data and you have daily observations, then you could do a similar thing and compare the results to what your model is giving you and see if the model is performing well or not. So yeah, it depends. I think it depends on really what you want to do. On the other hand, I mean, if you are thinking about modeling it, that's a whole different thing, right? You could run your own model, right? Not a global one. I mean, these are run on like very, very high level supercomputers. But you could run your local one and see how your local model, let's say along the Gulf of Guinea, is doing compared to the global model and compared to observations as well. Does that answer your question, Daniel?
For what I'm thinking, I mean, I have a lot of work to do. I mean, that's my take-home message. So I have a lot of work to do. Yes. So thank you.
Yeah. So all of that is true. I think, Daniel, like what you were asking. So most models will give, if they have daily data, it'll be a daily average. So the time step is actually much higher in the model, or much more frequent than daily, but it'll average out and give you the daily output. But that's not always the case. Sometimes you get daily snapshots. But yeah, I actually don't know. I feel like it's a bit more of a complicated question to figure out how to compare snapshots and averages of daily data, for instance. It's a good question.
A lot of work.
I don't have a good answer. Yeah. Don't we all?
We all have work to do.
We all have a lot of work to do and a lot to learn too. There's a lot here, so we're all still learning.
I'm learning a lot from this actually, right? I mean, this is what you can. I've worked with global data a lot, and I wish that when I was doing my research, these tools were available.
Yeah.
Right?
Yeah.
I was struggling with Anna and co, trying to merge these faces together, and now you have all these nice tools to merge the faces
just does
and
it
tiles.
for you. Oh, my gosh. Yeah. And so that's what the goal of a lot of this is to make scientists' lives easier so we can focus more on doing the science than the coding.
Exactly. Yeah.
Yeah.
Yeah. We heard Dr. Abram.
Oh, was that for us, Kwesi?
No, I think he was talking to somebody else.
Okay, I'm going to mute you then. Yeah, absolutely. And that's one of the reasons we really wanted to make this Jupyter Hub available as soon as possible, even though the company is still, just started putting these up. So, but we kind of want as many people to have access to these tools as possible. So when I started my postdoc, I said, well, maybe I should just look at, a certain region in the ocean and it will be easier. My postdoc advisor, who's really big on all of these tools, said, no, you can do it globally just as easily. Like when you have the tools, you don't even have to pare it down. I mean, you might want to for other reasons, but not just because of computational difficulty. So I thought it was just a slightly different way of thinking. I thought, oh, wow, okay. Yeah. So I'm going to try and find some more tutorials and add them to our Jupyter Hub here. I got some feedback at a previous session that, and many of you, I think, are beginners with Python, which is great. And I really kind of dove into a lot of these really more advanced topics, because I just kind of want you to see them, and you have the recordings. So maybe at some point in the future, if you feel like you understand more, you could go back and hopefully understand more of what I'm going through. But I'm going to try and find some tutorials, maybe more beginner friendly, that I could just add here from other websites. So that might be helpful. And if there are other examples you'd like to see, I can do my best to try and get them up on the hub. I don't have nearly as many tutorials next week, but I do have a Q&A session, which is basically anyone can come to it. I won't really have anything planned to go through, but you can come with questions, and I can, walk through whatever you're interested in during that time. Is there any more? Any other comments or feedback for me? I'll take good and bad.
So Paige, this is probably off distance. Do you think COESSING could have some kind of funding to keep this hub going for quite a long time or something like that? That would have been great if we have some money, right? Because it's a great resource, I think.
It's a really good resource. Yes.
Yeah.
So a few months ago, when we were thinking about doing this, one of my main concerns is that we don't really want to provide this great resource and then just get rid of it, because that's not really useful to all of you. So the goal is absolutely to do that. And I think I'm still trying to understand how much this costs. And a lot of it depends. So running a dask cluster, for instance, is very expensive. And I don't know what that means. But this for me is kind of a trial, and I will hopefully get more information at the end of this school to know how much it costs. And we're all kind of, it's not, others have better idea, but we're all kind of trying to figure out this new funding model and how to know how much it costs when you're doing on demand. And so absolutely, that would be the goal. And it might be something that I'll try and look into this year. We are being funded through a few grants. I need to figure out exactly which ones before I say, but I will definitely advertise those. And so the goal is to keep it open. I think it will depend how many people are using it, and all of that. So I think there's a chance that we can keep this open for the next year, until the next school at least. But I said I don't want it to go down after the end of the school, so it should be up for a few weeks at a bare minimum, and then we should know more about the cost and how much funding we have, and maybe this is something that we should talk to Brian about and make part of the. But I think I agree, and this may mean we need to seek out some different funding opportunities, but I think I'm hopeful that we could actually find some good funders for this kind of thing. That's a good question. That's the best I can do. And we decided to give it a try. And so I think for now, keep using it, and I will give plenty of warning when it will go down, or start a discussion about that, either on Slack or on email.
Right. Okay. Thanks.
Yeah. And I think if any of you, like at the moment, this is very much set up for, ocean, climate, maybe atmospheric modeling, and data analysis. So especially those of you in that space. So in different fields, there may be less of a need for using very large data sets. But in certain these fields, like when you're, analyzing very large models, if anyone here, that a lot of you have been at, a lot of my tutorials, so I can tell that you're all the eager ones. If any of you are interested and really want to keep access to the Jupyter Hub, please let me know, because I'd say there's a chance that we would have to limit the number of people. But I would want to make sure that everyone who's really excited about, doing this and really using the data sets available on the cloud and the computing available, that we can keep it up for you. So yeah, contact me on Slack is the best way. I monitor Slack every day, so almost every day. So that's kind of the advertisement. So anyway, I'd love to hear from all of you on any of these things, and don't be shy to ask questions. And we all have to start from somewhere. So even if you're a beginner, but you're like, no, I really want to learn this, that's great. We can make that work. Okay, so we have like 4 minutes left. Should we take another photo? I really like photos.
Let's do.
All right. I think I will.